In Module 2, we'll spend a lot of time talking about the properties of solutions. In Lecture 1 of this module is, not surprisingly, some introductory material on solutions. When we think about something dissolving in something else, we are referring to the solution process. And in this process, a solute dissolves in a solvent to form a solution. I've underlined these three words because keeping track of each of them and what they really mean will become important later, even when we start doing calculations. The process of dissolving is sometimes simply called dissolution or even solvation. And when water is the solvent, the dissolving is oftentimes called equation and or hydration. Let's make a solution, or at least pretend to, and we'll keep this simple. Suppose we want to dissolve 10 grams of sodium chloride in 100 grams of water to make 110 grams of solution. So here sodium chloride would be the solute, water of course would be the solvent, and when the sodium chloride dissolves in the water, we'll have a solution. This cartoon is going to try to help us with this thought experiment. The beaker all the way here on the left is supposed to represent our 100 grams of liquid water, in other words, our solvent. We are then going to add 10 grams of solid sodium chloride, which would be our solute, and here we're wisely using a funnel so we don't spill any. And you'll notice that the sodium chloride drops into the water and hasn't quite dissolved yet because we probably need to stir it. And when we stir it, the sodium chloride particles seem to disappear. They're not disappearing in actual fact, they're just dissolving. And we'd have 110 grams of aqueous sodium chloride, or in other words, 110 grams of sodium chloride solution in water. We oftentimes don't draw cartoons to try to show the reader what we're doing, so we'll write an equation. So this would be an equation we might write that would represent what we just saw in this cartoon. Solid sodium chloride is dumped into water to make, and dissolves, to make a solution of sodium chloride or aqueous sodium chloride. Here we don't really know where to put the water in the equation, but we want to tell the reader that the solvent is water. We kind of know that because this says AQ, which means dissolved in water. But sometimes we emphasize that by putting H2O liquid over the arrow just so everybody knows the solvent was water. Now, if we view the dissolving of sodium chloride in water at the atomic and molecular level, it could reveal several processes that absorb or release energy from the surroundings. And this absorption or release of energy actually helps determine whether or not one thing dissolves in another. Many of the processes that give off energy or absorb energy originate from the various types of intermolecular forces that we discussed in Module 1. Here's a very complicated looking diagram, and the only reason it looks complicated is because we want to show you the best we can here with what we've got to work with, what the dissolution of sodium chloride might look like at the atomic and molecular level. So look on the left here, and what we have is our solvent water. So you can see oxygen with 2 hydrogens attached. So these are individual water molecules minding their own business before they have to start dissolving sodium chloride. And this cube here is actually representative of a crystal of sodium chloride right after it falls into the water. So there's no dissolving taking place yet. It's just been thrown in the water. The spheres that make up this cube are representative of the two different kinds of ions. So here the purple spheres are sodium ions and the green spheres are chloride ions. You notice that chloride ions are larger than sodium ions. That would have been something you covered in General Chemistry 1. Well, the solvent-solute interactions, meaning the interactions between the water and the sodium chloride, start to kick in here and the sodium chloride starts to dissolve. So you can see that we have a group of water molecules that have basically captured a sodium ion. And here's another picture right here of a group of water molecules capturing a sodium ion out of this crystal lattice. And there's a blown up view here of what appears to be 6 water molecules with their oxygen ends pointing at the sodium ion, and this is called a hydrated sodium ion. These little red dots don't represent necessarily the kinds of bonds that we're used to seeing, but they turn out to be bonds that we'll later call coordinate covalent bonds. And also the water molecules are breaking off chloride ions from the lattice. And you can see that in miniature and then blown up. And interestingly enough, here we have the water molecules using their hydrogen ends, which would be the more positive ends of the water molecules, hydrating the chloride ions. These are definitely not bonds here. We'll talk more about that in the future. Eventually, the water molecules pick apart the entire crystal lattice, and we have sodium ions and chloride ions hydrated in solution and separated from each other. Now, it takes energy input to overcome the lattice energy holding the sodium chloride crystal together, and it also takes energy input to get the water molecules to become interested in the sodium chloride, because remember, water molecules are attracted to each other with dispersion forces, dipole-dipole, and hydrogen bonding forces. So in a sense, we have to pull the water molecules apart, or they have to be pulled apart from each other in order to go after the sodium and chloride ions. This has to be worth it for them, and it turns out in this case it is. The energy released through the ion dipole forces between the ions and the water molecules helps to compensate for all the energy input needed to break up the sodium chloride lattice and to get the water molecules to be less interested in each other and more interested in dissolving the sodium chloride. Now, consistent with this more complicated graphical description of the dissolution of sodium chloride in water, the equation from the previous slide can now be expanded to look like this. Solid sodium chloride dissolved in water to give aqueous sodium chloride, which in reality means separated, hydrated sodium ions and chloride ions in solution. There are many other types of solutions besides just solid ionic solutes like sodium chloride dissolving in water. As with ionic solids dissolving in water, each of these other types of solution processes are governed by intermolecular forces and net overall energy changes resulting from the mixing of the solute and the solvent. What we're going to find out is that a solute will not dissolve in a solvent unless it's energetically favorable to do so. Let's look at some of these other types of solutions. You could have a molecular solid solute dissolving in a liquid solvent instead of just an ionic solid. And some examples here would be table sugar, which is a molecular solid dissolving in water. We know that sugar dissolves in water. General Chemistry 1 would be where you'd find the definitions of a molecular solid versus an ionic solid. But just as a quick review, a molecular solid would be a substance where it can exist as individual molecules. Sodium chloride is not a molecule. It's really just two ions stuck together. Table sugar exists as a molecule. And typically molecular solids are held together by pretty much mostly covalent bonds. And a lot of carbon and carbon-hydrogen compounds would fit the bill. So table sugar is a great representative of a molecular solid dissolving in a liquid solvent. Para-dichlorobenzene, which is a very smelly organic molecular solid, is in fact not soluble in water, but it will dissolve in a liquid solvent called acetone, which you've probably used in a lab in the past. How about a liquid solute dissolving in a liquid solvent? Well, this is easy. Methanol, an alcohol, wood alcohol, dissolves in water. Liquid solute, liquid solvent. Chloroform, which is not soluble in water, does dissolve in the organic solvent acetone. And just as an aside, we're going to find out that when we have a liquid solute and a liquid solvent and they dissolve in each other, we say they're miscible. That word will come up again. How about a gaseous solute in a liquid solvent? Well, the easiest example would be carbon dioxide gas dissolving in water. Think soda pop. Nitrogen gas, which is nitrogen's nonpolar, is quite soluble in chloroform because chloroform is barely polar. So we've got a gas dissolving in a liquid. How about a gas solute in a gaseous solvent? Well, easy to come up with an example here. The atmosphere could be considered essentially a solution of oxygen acting as a solute in a nitrogen solvent, since nitrogen is the substance present in greater molar quantity in the atmosphere. How about a solid solute in a solid solvent? That seems pretty silly. If you melt them first, you can get them to dissolve in each other, and when they do, it's basically a solid solute in a solid solvent. Metal alloys would be a typical example. So bronze could be thought of in its most basic form as tin dissolved in a copper solvent. Now, as you most likely have observed in lab or in everyday situations, it is often the case that physical mixing of two substances does not result in a solution. For example, although the ionic solid, sodium chloride, dissolves readily in water to make an aqueous solution of sodium chloride, the ionic solid silver chloride does not dissolve in water to any appreciable extent. Now we can express these facts in equation form. So before sodium chloride dissolves in water to give aqueous sodium chloride, and then hydrated sodium and chloride ions dissolved in water. And if you look this up in a handbook, you'd find out that sodium chloride is very soluble in water, but it's not infinitely soluble. At 25 degrees C, about 36 grams of sodium chloride will dissolve in 100 milliliters of water. If we write the same equation for silver chloride, and we go into a lab and actually take silver chloride and put it in water, we'd find out that it looks like it just doesn't dissolve. So what we write here is NR, meaning literally no reaction. But in this case, it just means that silver chloride does not dissolve to any significant extent. I have a little note here. And when we say that silver chloride is insoluble in water, it does perpetrate a little lie, because we find out later that a tiny amount does dissolve, but it's so tiny that if we say that silver chloride is insoluble in water, we're not really lying unless we take it to the extreme. In any event, sodium chloride dissolves in water, silver chloride effectively does not. Now here's a second example. Although the molecular substance methanol, this is methanol liquid, is very miscible, in other words soluble in water, the molecular substance hexane is not miscible with water. It just will not form a solution with water. Now, as in example 1, we can express these observations in equation form. We could say, look, methanol, liquid methanol dissolved in water, they dissolve, they're miscible, we have aqueous methanol. Hexane, liquid, throw it into water, no reaction. In fact, the hexane, which is less dense than water, will separate out, and if you mix them together, the hexane, it looks like they're trying to dissolve, but the hexane will just separate itself out from the water and float on top of the water. Even if you stir it and shake it, you've probably seen a similar situation with oil and water. Now, in order to better able to predict, be better able to predict whether or not one substance will be soluble in another, we need to take a qualitative and even semi-quantitative look at the specific energy changes involved in the solution process and relate these energy changes to the relative magnitudes of the solute-solute intermolecular forces, the solvent-solvent intermolecular forces, and solute-solvent intermolecular forces. Bottom line, energy changes when making solutions are important. We want the solution process to be energetically favorable. Whether or not it's energetically favorable depends on the types of intermolecular forces operating in the solvent, in the solute, and between the solvent and the solute. So we can begin this by examining a predictive model that's typically introduced in high school chemistry. Like dissolves like. So this method is pretty useful under particular circumstances. And let's elaborate on what we mean here. Like dissolves like basically means that the more similar the intermolecular forces operating between the solute molecules are to those operating between the solvent molecules, hope I said solute here, operating between solute and operating between solvent, the more soluble the solute is predicted to be in that solvent. Now this rule of thumb has become particularly useful for situations where both the solute and the solvent are molecular substances. Let's do some examples here and we'll show you what we mean. Let's think about the methanol water example where we said methanol, wood alcohol, readily dissolves or is miscible in water. The like dissolves like model would predict that. So we have liquid methanol interacting with liquid water and we get dissolved methanol or aqueous methanol. And with this chart, we might be able to show you what we mean by the like dissolves like model predicting this. What we have here is a methanol solute, and these little dashed lines between two formula units of methanol are supposed to represent the intermolecular forces in methanol. And we'd also have the intermolecular forces between the solvent molecules, water, and then intermolecular forces between methanol and water if they dissolved in each other. Well, what are the intermolecular forces operating between methanol molecules? Well, dispersion, of course, dipole-dipole because methanol is polar, and hydrogen bonding. We've got hydrogen attached to oxygen. Well, not coincidentally, water has the same types of intermolecular forces. And As a bonus here, when we think about methanol interacting with water, we've got the same types of forces that are operating between the solute molecules and between the solvent molecules. Dispersion forces, dipole-dipole, they're both polar, and hydrogen bonding, they're both capable of hydrogen bonding. So the solute-solvent intermolecular forces here are similar to those operating in the solute and the solvent, which themselves have similar intermolecular forces. So all of this would say, hey, like dissolves like would predict that methanol should be soluble in water, and it is. How about hexane in water? Well, like dissolves like correctly predicts that hexane would not be soluble in water. Well, why is that? We'll use a similar chart. We've got hexane intermolecular forces, that would be the solute, intermolecular forces between water, and any potential intermolecular forces between hexane and water. Now, hexane would have only dispersion forces. Hexane molecules are nonpolar. You might say, how would I know that? Well, in the previous module, I think we talked about hydrocarbons as being nonpolar. We know all about water and its intermolecular forces, so right away we see very dissimilar intermolecular forces. They are probably not good candidates to interact with each other and dissolve in one another. And on top of that, the only thing that would attract hexane to water would be dispersion forces, because water's polar and is capable of hydrogen bonding. Hexane is capable of neither one of those. So we say the solute-solvent intermolecular forces or potential forces are nothing like the forces between water molecules. They are a little bit similar to the forces, of course, between hexane molecules. But overall, the solute, solvent, intermolecular forces are just very dissimilar. So like dissolve like would say, no, we'd probably predict that these would not be soluble or miscible in each other, and they are not. Now, the like dissolves like model can be used to explain some interesting solubility trends. For example, consider what we call the condensed formulas and the 2D structures, two-dimensional structures, of the two alcohols, methanol and hexanol, shown below. Now keep in mind in these diagrams that chains of carbon atoms attached to hydrogens, hydrocarbons, are considered nonpolar. I mentioned that on the previous slide. So let's look at methanol. It's a simple molecule. The condensed formula shows just a very short portion of it has carbon attached to hydrogen. Here's the two-dimensional Lewis structure. And then there's the OH group called the hydroxyl group, and that's fairly polar. So in methanol, the polar OH group has a large influence there. And so we say methanol is fairly polar because the influence of this non-polar end of the molecule, carbon, hydrogen, is just not very large. Hydroxide rules the day. I shouldn't say hydroxide, the hydroxyl group rules the day. Hydroxide is different than a hydroxyl group. Let's look at hexanol. Hexanol is in the same family as methanol. It's an alcohol, carbon chain with an OH group, but you'll notice in hexanol that the carbon-hydrogen groups pretty much dominate the molecule. And since carbon-hydrogen groups are non-polarish and the hydroxyl group is polar, the dominance of these non-polar-ish carbon-hydrogen bonds, this carbon chain, really rule the day, meaning hexanol is just not very soluble in water because of the overwhelming presence of those non-polar carbon-hydrogen groups. The textbook has a chart of some the solubility of some alcohols in water and in hexane. So we're switching gears from the top of the slide here. So let's take a minute to talk about what this table is showing. It says, let's take methanol, and we know that it's soluble in water, and it's soluble in hexane, a nonpolar solvent, but not very much. Ethanol, which has a longer carbon chain, is still soluble in water, but it's very soluble in hexane, which is a nonpolar solvent. The longer carbon chains for propanol, still soluble in both water and in hexane. So the 3 carbon chain here makes it soluble in hexane. The hydroxyl group makes it soluble in water. But when you get to butanol and pentanol, you'll notice that the carbon chains are becoming so long that butanol is now becoming less interested in water, but it certainly is very interested in the nonpolar hexane. So again, note that as the attached carbon chain increases in length, the solubilities of alcohols in water decrease significantly. Another way of describing this trend is that the carbon chain portions of the alcohols are hydrophobic, which literally means water hating. And the OH portions, the hydroxyl end of the alcohols, are hydrophilic, meaning water loving. So there is increasing hydrophobic character, increasing carbon chain character, going from methanol to propanol to hexanol, thereby decreasing the solubility in water. And although it doesn't seem to show a smooth trend here because it goes from slightly soluble to just really soluble, the point here is the alcohol with the longer carbon chains do dissolve in the nonpolar hexane. Ethanol and propanol are interesting cases. The hydrophilic OH groups in these alcohols, the water-loving parts, have enough influence to allow good solubility in water, while the hydrophilic carbon chains are long enough to also allow solubility in the nonpolar solvent hexane. Here's another application of the like dissolves like concept. Now, acetone is a versatile solvent found in most chemistry labs. The various ways to display the formula and/or structure of acetone are below. So this would be considered the condensed formula of acetone. Here's a two-dimensional Lewis structure. So we have 2 carbon-hydrogen groups. These are literally called methyl groups attached to a central CO group. If we condense down the Lewis structure and write it a little more succinctly, we'd see it written like this. So here are the methyl groups. Chemical drawing software will often make what looks like a mistake and have carbon here attached to these 3 hydrogens. That's not right. A chemist reading this would read it like that, because it's silly to think that carbon would attach to 3 hydrogens when it's already attached by double bond to oxygen into another carbon. Here's a 3D model, the best we can draw for acetone, and here it shows that the molecule itself is polar. And here's a 3D space filling model showing the polarity of the acetone. Okay, acetone's called a versatile solvent because it's very soluble it's miscible in both water and a large number of organic or carbon-based solvents. So here's a larger picture of the 3D structure. So we say, look, its water solubility comes from the overall polar character and the presence of an oxygen atom that can form hydrogen bonds to the OH group in water. So you might find a chemist describing the oxygen end of acetone as the hydrophilic part of the molecule, water-loving part. And this 3 carbon chain here. So we have these 2 carbon hydrogen ends, and we have a 3 carbon chain, including the carbon in the middle, allows it to be soluble in a large variety of organic solvents, non-polar type solvents, or non-polar-ish. And we'd say that the 3 carbon chain in acetone is the hydrophobic part of the molecule. In a chemistry lab, you'll often see acetone used to dry glassware. Clean but wet glassware is rinsed with acetone. The acetone dissolves in the water, and the solution form evaporates quickly, leaving dry glassware. And it's also often used to rinse leftover organic solvents from the glassware. If you do use acetone in a lab, most likely the acetone will be in the fume hood, because you don't want it out in the open lab where there might be open flames, because acetone is, especially the vapor, of course, is unbelievably flammable, and it's highly volatile, which means it evaporates easily, the vapors crawl around, and it's just as bad, or it's not worse than gasoline. So you keep it in the hood. Let's try to apply this like dissolves like model to ionic solids dissolving in water, using our previously discussed examples of sodium chloride and silver chloride. So we said sodium chloride is soluble in water. We draw up a table to analyze intermolecular forces. The solute-solute interactions are simply dispersion and ion-ion forces. This is just the plus and minus charges holding the lattice together, and of course dispersion forces operate everywhere. The solvent-solvent intermolecular forces we know well in water: dispersion, dipole, dipole, and hydrogen bonding. And if we think about the interactions between the solute and the solvent, they would involve dispersion forces and ion dipole forces. You look at this and you say, well, I don't know if these forces are exactly identical. If you think about it a little more, they're pretty similar. It could be argued that these are pretty similar forces because they all involve attractions of very significant positive and negative charges. Maybe not full positive and negative in all cases, but significant positive and negative charge. The solute-solvent intermolecular forces are also somewhat similar to those operating in the solute and solvent, because you've got a charged ion interacting with a fairly, or I should say partially charged dipole. So it's not too surprising that sodium chloride would be soluble in water, like dissolves like. The intermolecular forces operating there are all fairly similar. Well, the same could be argued for silver chloride. And of course, spoiler alert, we already know silver chloride is not soluble in water, which is a little perplexing, because when you do the analysis of the intermolecular forces, it looks a lot like the analysis for the sodium chloride. Looks pretty much just like the sodium chloride example. However, silver chloride's found to be essentially insoluble in water. Well, that should be disappointing. What do we say? Well, like dissolves like model has its limits, and it certainly doesn't seem to do a very good job distinguishing between sodium chloride dissolving in water and silver chloride dissolving in water. In part 2 of this lecture, what we're going to do is start looking at energy changes and energy absorption and energy release in a little more quantitative way. So for now, you might remember that like dissolves like is an okay starting point. It generally works much better when we're talking about molecular substances dissolving in solvents. For ionic substances, it doesn't always work so well. And we're going to do a little bit deeper analysis of some energy changes that occur in part 2 of this lecture.